Okay, so we're starting. The topic of today's presentation are three famous models, which are Transformer, GAN, Generative Adversarial Networks, and Diffusion. Uh, well, this is page about me, the speaker. So I'm CTO, co-founder of a startup called Beta. Many years of experience in software, data science, building teams, originally PhD in mathematical modeling. Current interests are crypto accounting, cloud, fintech, generative AI. That's why this lecture. And you can easily find me because my last name is quite unique. So combination of left selector, you can easily find me. Uh, how generative AI creates new content? Somehow when I'm asking people this question, what is generative AI? People, yeah, hi, can you please mute yourself? Okay, people get lost. So they think that generative AI generate something from thin air, from nothing. And it absolutely not how it works. So generative AI systems first learn from large amounts of existing data, and then using this latent representation of this data and some randomness to generate new examples. But they're derived from terabytes of data which it kind of digested and assimilated. Okay. Uh, about these models, transformers, GANs, and diffusion models, they are absolutely everywhere. And here I want to give an example of DALI 2, which is an OpenAI system which can generate images. So you tell it what you want on the image and it can generate. And here are some examples of what it can produce. So the interesting thing about DALI 2 is that it uses all three types of models inside one system. So DALI 2 is a large language model. It's OpenAI, and it generates images from text descriptions. It was announced a year ago, and it is the second version. Before it was DALI model. And by the way, this is Dali, Salvador Dali. And it was released a year before that. So it was trained on massive data sets. It learns the relationship between words and images to generate images from text. And it's very easy to use. It's a website. You just go there, you give a description, and it will generate an image for you. So it uses Transformer GPT-3 language model, which was developed by OpenAI itself, to convert text into some internal representation. It uses diffusion model to generate images and big GAN. So there is big GAN and there is a giga GAN. So this particular one is big GAN, which was generated by Google AI. So it is a deep convolutional generative adversarial, not whatever. I'll explain what GANs are later. But just an example that all three types of models in one system. So first, I will talk about transformers. And first, a little bit history. And this is more about translation, like famous Google Translate, how people came to this and how transform architecture appeared. So if you're thinking about translation, let's say you have some sentence, it consists of words, you can take a dictionary and you can translate each word and substitute, and you will have a translation, although very, very bad. So this is a very naive translation. Then what people were doing, they were writing programs as long as like 500,000 lines of code to do translation. And this translation program will have a lot of if-else statements. Like if this word is surrounded by in a company with another word, then it has this meaning. And if it is in the beginning of sentence or if it is the end of, like a lot of if-else, a lot of knowledge about the language, a lot of like idiomatic knowledge, but it's huge and it was not very good. Then what happened, and it mostly when Geoffrey Hinton was invited to Google, and Google did a lot of work. I want to mention several steps. One is word2vec. It was 10 years ago, and the word2vec model was using embeddings. They are not invented embeddings, but they use them successfully. So the idea is that the meaning of the word is uh, uh, can be defined by its friends, its neighbors. So if you have two words which may be spelled differently, but they have the same meaning, you could expect that in the sentence they may be have the same neighbors, the same surrounding, the same before and after. So these words can be substituted in the sentence. And the idea of this model is to create vectors. So each word is represented by a vector. Vector may have 100 numbers in it. It's a numeric vector. And then you train the model. It's a two layers neural network, so that similar words will have similar vectors, and these vectors are trained from neighbors of the word. So you have a lot of text, you go take the word, you take neighbors before and after, they have their own vectors, and then you adjust the vector of the central word based on these vectors, and you repeat the process iteratively multiple times. And it's very interesting because after you train this network and you have vectors, and if you look at like king to queen and man to woman, you basically can do vector operations with these vectors. Very interesting. But again, it's kind of primitive because it's just about the word, the meaning of the word, not so much about the sentence. And it only takes into consideration the closest neighbors, not like what if you have a sentence and then in the beginning you have don't, like do something, whatever, right, which changes the meaning of the sentence. So the next iteration was attention and transform architecture. So we're talking about 2016, 2017. Google created this Google neural machine translation system, which was using attention. They published an article, Attention is All You Need, in 2017, but it describes what was done in 16 and why it's called Attention is All You Need, because in this system they're using attention mechanism exclusively, doing away with the need of recurrence and convolutional entirely. So interesting idea. I will describe attention in details like in the next slides. But the main purpose is that if you have a long sentence, uh, you you cannot just, like in previous, like in recurrent networks, in LSTMs, long short-term memory models, you would pass information from left to right, um, but it's kind of trying to pump too much information through the same channel. Whereas in this model, if you have n elements or tokens in the sentence, they create a matrix of n by n, and they try to figure out which words are important, and they assign them scores, and they do it over and over again. It's interesting algorithm, but they if you have this don't in the very beginning, they will not lose this information. Like this algorithm takes care of all that. Very, very interesting. So attention, the article, the Google Translate based on the attention mechanism, and this architecture is called transformer. And the reason why it's called transformer, because you transform one sequence of something, like for example of words, of tokens, into another sequence. Like you translate from English to French, for example. It's a transformer. But later, transformers are now used for many different purposes. But the whole idea, you have input and you have output, and you transform from input to output. Another interesting thing about transformer architecture is that the calculations can be parallelized. So it can be made very effective, as opposed to recurrent neural networks or whatever, where you have to do things sequentially, like from left to right. Okay, so this is a little bit of timeline, historic line. So transformer. Transformer using attention mechanism, and well, in transformer it's called self-attention. So let me go through some steps and some terminology. You have input, which is consisting of words, and you need to convert these words into some sort of numeric representation, into vectors. So this is called input embedding, right? Next, what's happening, you calculate vectors, internal helper vectors. So it's called query vector, key vector, and value vector, right? And these vectors computed for each word and using separate weight matrices. Oh, now you have separate matrices. Then you calculate the score between each word using its query vector and key vector of every other word in a sequence. So that's where you're creating n by n matrix. So this score reflects the relevance of other words to the current word. Then you do normalization, well, which is normal, right? And you're using softmax function. And then you calculate the output vectors when of scores, whatever. The output is a weighted sum of value vectors where the weights are softmax scores. Okay. In essence, this attention score calculation process allows the model to decide how much attention each word in a input sequence should pay to every other word in the sequence. Okay, so this is the main idea. Now, I mentioned here three vectors, query, key, and value vectors. And they are calculated using three separate weight matrices, which, again, at the beginning are not known. They have to be learned during the training. For each word or token in the input, these weight matrices are used to transform original input vector or word embedding into the query, key, and value vectors. So these are their definitions. So Q, K, V, query vector, key vector, value vector, right? So query vector representation of the current word or token, it's used to score relationship with other words. Key vector representation of all other words or tokens. Each word in the sequence has corresponding key vector, which is compared with the query vector to compute the attention scores, right? So Q is about the word itself, K is about all others, so you can calculate the relationship. And value vector is a final representation of other words or tokens in the sequence. It is used in the final computation of the new representation of the current word. It doesn't influence the attention scores, but it's weighted by them to provide the output. Okay. It actually will take more time to absorb all that. I'm not trying to actually explain things clearly, but I just want to show you what's inside. Okay, what I really recommend you to do, like really, is to go to this link, and this is absolutely best visual explanation, illustrated explanation of how transformer works. It has a lot of pictures, so you see, for example, je suis étudiant. So this is French, it encodes, then it decodes, and then it becomes English. And then it shows that encoder actually consists of multiple steps and decoder consists of multiple steps. And there is a connection between encoder and decoder. And then each of those encoders, let's say, it consists of two layers. One is a self-attention layer and another is feed-forward neural network. And in the decoder, each piece consists of three. So here, each one of those decoders consists of three. And again, you have self-attention, you have feed-forward, but in decoder, you also have encode-decoder attention. So you're trying to relate between decoder and encoder, a kind of a feedback. If something was very important in encoder, you should also make sure that it is important in decoder. Okay, then it goes in more details how things, like I really recommend this article. It's very well illustrated, but you will need to spend more time than we have at this presentation. So I just copy pasted some pictures to show you. Okay, so encoder and decoder, you just seen it on these pictures, and I just want to like say, okay, there are encoder and decoder. So encoder encodes the word into a series of into vectors, words into vectors, or tokens into vectors. And there are, in encoder there are two sublayers, which I just told you here. This is self-attention and feed-forward, and in decoder there are three of them, right? So, and you can see it on this diagram. So this is encoder, it has two layers, and this is in decoder, you have three, and there are multiple of them. Okay, next, I'll answer several questions. So, how transformers architecture deals with the very long sentences? So, they try to take the whole sentence at once and convert it, right? But if a sentence is too long, then they have to do something about it. They can split it in pieces. They can process like piece at a time. They can use some sort of sliding window. There are multiple approaches, multiple articles. It really depends on the task for which you use transformer. What are the sizes of the matrices? Remember I told you about matrices. So when you encode words into vectors, what is the size of the vector? So the size of the vector is actually quite big. So it may be 500, it may be much more. So here, for example, I provide some numbers for GPT-3 model, generative pre-trained transformer, right, from OpenAI. And ChatGPT was originally based on GPT-3, and now it's on GPT-4. But look at the dimensions of hidden layers, right? So, and this is sequence length, default sequence length. In ChatGPT 4, it can go much longer. It can go 8,000 and even like 32,000. But the vector length, you see, it's pretty long, right? And then so n is sequence length, and size of the vector is h. It's a hidden vector. So these are two numbers. In the original transformer model, the sizes of query key and value matrices are n times h, so they're not squared. But the size of attention matrix is n by n. Why? Is because it is each word in the sequence against each other word, and the n is the length of the sentence, of the sequence. So if the input sentence is short, it can be padded to the length n. If the input sequence is longer than n, then we have a problem, we have to do something. We can brutally truncate it, we can use sliding window, we can process piece by piece, chunking, multiple articles, multiple solutions. Okay, I want to say a few words about BERT. So BERT is bidirectional encoder representations from transformers. What it means is that in the transformer architecture, so you have encoding and then you have decoding, right? So BERT is only using encoding. So remove the decoder. So what encoding does, it converts words into some internal representations. So that's what it does. Encode the representations from transformers. So BERT is just this piece of transformer architecture, and bidirectional or bidirectional, how you say. It means that usually when you do translation, you translate from left to right. But in BERT, it takes into account both left and right at the same time, treat them equally. So that's what it is. And the usage of BERT is that you encode your data into some internal representations, and then you use those latent representations to do something else. You can do some sort of classification, some sentiment analysis, or whatever. So there are a lot of applications again, but just to understand that BERT is related to transformer, but it's a different model. It's kind of part of transformer. Okay, next I want to talk about GANs, Generative Adversarial Networks. And this slide I used for several years now. A young good fellow, about 10 years ago, 2013, right? So he was in Montreal, and his thesis was on actually building the generative adversarial network. So this is a very, very simple explanation. So the network actually consists of two networks. I call them police detective and artistic criminal. So they both get access to the same images. So let's say you have images of cats and dogs. And what artistic network does, it takes those images and it randomly combines them, making some sort of fakes. And then these fakes or real images are shown to the police detective. And the police detective, which is also called discriminator, its task is to tell whether it's a real image, is it a cat or a dog, or it is a fake. And his decision, of course, is passed to the criminal. So criminal says, aha, he doesn't know how to do that. Let me feed him more stuff. And of course, police detective also gets whether he was right or wrong. So they both can adjust their policies, how they do their stuff. So if they play this min-max game long enough, the artistic criminal learns to make very good images, which is very difficult to distinguish from originals, and police detective becomes very good and still spotting that this is a fake. Let's say you use images of human faces, and after playing this game for a long time, the artistic criminal learns to generate very good pictures of human faces which are fake, which don't exist. There is a website which is called thispersondoesn'texist.com or whatever. You can just Google it and click, and it shows you faces, and these are all synthetic. And it's very difficult to believe because you can see their eyes, you can see like brows, you can see every hair, like they're absolutely alive. How is it possible? But again, it's not created from thin air. It's created by being trained on terabytes of data, on millions of images. So this is generative adversarial networks. They were created first to generate images, and they are famous for being able to generate images. So this is again another description of the same. So generative adversarial network. Why it's called adversarial? Because these two networks are in adversarial relationship. One is trying to win, and well, they're both trying to win. They're against each other. Generator and discriminator, two networks, right? A generator is the criminal, artistic criminal, and discriminator is the policeman. So generator, discriminator, two-player min-max game. So okay, it describes the same thing. So these are some examples, some variations of GANs. I told you about big GAN, which is used in DALL-E 2 to generate text from images from text, sorry. And this is GigaGAN. So BigGAN was created at Google 5 years ago, and GigaGAN was created recently, about a year ago, by researchers from Postech, Carnegie Mellon, and Adobe. And this is absolutely amazing because, well, it's bigger, it has more than 1 billion parameters. It's very fast, so it can create 512 by 512 output in fraction of the second. So it's really orders of magnitude faster and better than previous generations of GANs. It can synthesize 16 megapixel in like 3.7 second. Absolutely amazing. There are some other variations of GANs. So if you're interested, you can look at them. Okay, the last type of model I want to talk is diffusion models. And this is something recent. Diffusion used for generative modeling, right? It can be used for image generating, image denoising, in-painting. So if you have like a hole in your image and you need to in-paint what was supposed to be there, right? Generate text, generate audio, all kind of stuff. So they originally were introduced in 2015, and they are basically Markov chains trained using variational inference. I will go in more details of that. So the goal is to learn latent structure, but again, this is for all generators. They take data, they learn latent structure, and then they combine different latent structures to generate the output. In computer vision, this means that the neural network is trained to denoise images blurred with Gaussian noise, whatever. So stable diffusion. You hear a lot, not just diffusion models, because there are multiple variations of diffusion models, but stable, specifically stable diffusion. And stable diffusion is a success story, which I will describe on the next slide. And so it's a text to image model. It's a specific diffusion model. It was created by Stability AI and some other players and made public last year, and it is open source and it's very good. So this is the story about Stability.ai. They are in London. Imad Mastak is the CEO of the company, and the company is growing fast, and he has very ambitions to become public, become the biggest generative AI in the world. And his model, because it's open source, attracts a lot of developers, a lot of variations of models being created. So it's a big thing. And so what it does, you can give it a text description and it will generate you the image. So for example, you can describe the image in style of Van Gogh, which you want to see, and it will generate you something like this. So this is a little bit story. There are many different types of diffusion models, like DDPM, denoising diffusion probabilistic model, SGM, score-based generative model, SDE, stochastic differential equation, and each type has its own advantages and disadvantages. Stable diffusion is not one of them. It's not a specific model, but rather a general approach to diffusion models. It's using noise distribution, which is stable. And so the question is why we need noise in the first place. I will go to it in the next slides. So it makes possible to train diffusion models more reliably and efficiently because of its stability. Okay, next is what's happening under the hood. That's not exactly what's happening under the hood, because we're not actually noising image, we're noising latent vectors. But whatever, that's people like show how, like, to give some sort of illustration of what's going under the hood. So let me try to explain what's going on. So stable diffusion creates images from text. Stable diffusion can generate high quality images, indistinguishable from real photos, and it's smaller than Big GAN or GigaGAN. It's using less than a billion parameters. So these are some good links in the video which I recommend. Here I tell what we do, how we train, and then how we actually use it, right? So when we train, we get a lot of data, and each piece of data, it's a tuple. It consists of text and image. So text describes the image. So we have a lot of those couples. And when I say a lot, I'm talking about like hundreds of million. And what we do, we take text and we encode it the same way as it's done in transformer. We create a latent vector from the text. We also encode image and we create a latent vector of the image, right? So you see, we create latent vector for text, we create latent vector for image. Then we want to do the opposite operation. We want to decode, learn to decode from latent vector to image. So let's say we want from a latent vector of text generate the image which was behind this latent vector. And for this, the system is using what's called variational autoencoder. I should have made separate slide to explain variational autoencoder. It's a strange thing. Imagine that you have a network which has input image and output image, and in the middle you have like a bottleneck, like here. You see it become like how to say, more narrow, and you encode your image into small representation, and then you decode back into image, and the goal of the system is to being able to reproduce. It's kind of stupid, why you need to reproduce? No, but what's happening here, you create a latent representation which is kind of compressed, and then here you add a random number generator, so the system becomes more stable because of randomness. It learns how to do stable thing. Now, if you give it an image which has noise in it, on the output you may get image without noise, so it can denoise. So that's in fact one of the major applications of variational autoencoders. Um, anyway, so here we're learning to build latent vectors representing the pair of text and image, right? And then once we trained it, so here's what we do. Let's say we get the text and the system wants to create an image. So first it encodes text into latent vector. Then, well, it has latent vector, and it has this whole database of latent vectors based on the training data. So maybe it can just find the closest vector and just show corresponding image. But that wouldn't be right? Because that's we want to also include other vectors. We want to make some sort of superposition, right? So what's happening here? It uses this vector to condition a diffusion process, and diffusion process starts with the image which is basically completely random, and then it diffuses, it tries to get something, and then it goes over and over and over again using this latent vector from your text to get latent vector of the image to be close to each other, and output to be low noise as much as possible. So it's an iterative process. You apply diffusion to make it more generic. It's the same how you do it in variational autoencoder. You apply noise and then you remove it. And after you do it multiple times, eventually you get the output. The benefit is that it avoids overfitting on the training data. It doesn't try to just make a projection to one of the training points, right? It avoids local minima, but it's kind of slow because of that. So GANs are much faster. Okay, so this is kind of explanation about stable diffusion. These are just some pictures and GigaGAN versus stable diffusion, right? So I told about generative adversarial networks, how they are really great at generating images, and GigaGAN is literally 10 to 20 times faster than comparable stable diffusion. So for example, on NVIDIA A100, which is a GPU, it can generate image in like what is 1/7 of the second, right? Whereas other systems like stable diffusion takes much longer. You see, literally 20 times longer. So GigaGAN was created by these people. It's a billion parameter GAN, stable model like stable diffusion, DALI 2, Midjourney will trade on big data sets. So I was talking you, okay, GigaGAN is 6 times larger than largest GAN to date, trained by the team using this data set with over 2 billion image text pairs, 2 billion. And this one is with, no, it's million, sorry, image text pairs. So like billion training points, about billion or 2 billion here. Okay. And there are also open source text to image libraries. I here just provide just one, but you can find many, and you see how easy it is. So this is called DALL-E Mini. It's actually now it's called Crayon. Like DALL-E Mini is the old name for it. So it's easy as people install this library, and then you create generator, and then you generate. You see generate, and you just give it like what you want to see, and then you can like save it as an image, and that's it. So you can generate your own images from text by just using this. Okay, this is the end of the presentation. So thank you. I will stop the recording.